Very good. Well, welcome everyone to this year's installment of the Turkish Med Society's distinguished lecture series, or team series, I guess. So it's a great pleasure to introduce Yiannis Sakellaridis as our first speaker today, this year, from Johns Hopkins, whom I've had the pleasure to know for over 20 years now. So Yiannis received his PhD from Stanford in 2006, where we met and studied together. After his graduation, he spent time in Tel Aviv, Toronto, Athens, and Rutgers University of New Jersey, before moving to Johns Hopkins as a professor. He's held prestigious visiting posts at the University of Chicago and the Institute of Advanced Study in Princeton. He was an invited speaker at the International Congress of Mathematicians in 2022, and he was named the Fellow of the American Math Society this year for his contributions to representation theory and the theory of automorphic forms, which I believe we're going to hear about today. And for his service to the mathematical community, this includes many workshops and mathematical gatherings he organizes regularly, one of which is the Nisiros meetings, a Greek alternative to Oberwolfach gatherings. Equally importantly, he once organized weekly Kyriaki Porosphero meetings back in the days at Stanford, in which I was a proud regular participant. Well, without further ado, Yiannis, the stage is yours.
Thank you very much. Teşekkür ederim. Thank you very much for the invitation. I said it before 5 minutes ago, and let me say it again for anyone who just arrived. Please feel free to interrupt me. I have a blackboard behind me where I can explain things or talk about something else. The topic that I'm going to talk about today is very broad, and my goal is to give you a feeling of some conjectures that we formulated recently with David Ben-Zvi and Akshay Venkatesh. Because the formalism of these conjectures is quite heavy, too heavy for a colloquium, what I will try to do is I will try to keep it simple and reduce the formalism as much as possible, and just give you a nice idea that combines everything from harmonic analysis to geometric representation theory. Again, feel free to interrupt. And do I have 60 minutes, or how much do I have exactly?
Take 60 if you want. Yeah.
60? Okay. So, yeah, this is a picture from the Bosporus again, 2011 in my youth. And now let's get to the math. So we start with the Riemann zeta function that everybody knows. It's the sum of n to the minus s for all positive integers. And it can also be written as an Euler product. That means a product over the primes. In his unique paper on number theory, Riemann in 1859 proved the functional equation of the zeta function, which relates the zeta function at s to the zeta function at 1 minus s. And the analytic continuation, of course, because the expressions that I showed before are only valid for real part of s greater than 1. How did he do that? He did that by writing it as this very strange integral that you see on the left-hand side that a priori has nothing to do with the zeta function. What is the integral on the left? This is going to be the main focus of our talk today. Like, what are these integrals? Where do they come from? How can they be related to zeta functions and L functions? So let's take a look at this integral a little bit. I mean, to show the equality that you see here is quite elementary. You just need to know the definition of the gamma function. But how you come up with such an expression on the left, that's very mysterious, because a priori, the zeta function is defined in a completely different way. So what is this integral? This integral contains a series, which is called the Jacobi theta series. It's basically the Gaussian summed over the positive integers. And then you take this series and, well, the Gaussian together with a multiplicative shift by y. and then you think of it as a function of y, and you integrate it against y to the s over 2. What is y to the s over 2? Y to the s over 2 is a multiplicative character, a character of the multiplicative group. So this is something like Fourier transform, but for the multiplicative group, also known as Mellin transform. So Riemann wrote down the zeta function as the Mellin transform of this theta series, but now this theta series essentially has a Poisson summation formula that allows you to prove this functional equation. I will not show you the details, but this is the idea. And again, please feel free to interrupt me at any point. This integral representation of the zeta function was reformulated in the 1950s by Iwasawa and Tate in terms of the so-called ring of Adels. Now, if you haven't heard this before, this may be, you might think that this is too much to absorb, but this is actually, the idea is very simple. You embed Q in essentially the product of all its completions. So one completion of Q is R, which I will write as Q infinity, but there are other completions of Q, which are the p-adic numbers associated to each prime number P, and they're defined as follows. They have to do with solving with congruences. They have to do with congruences. So the p-adic integers Zp are an inverse limit of the quotients of Z by P to the N. And this is a topological ring. Two elements in this ring are close to each other if their difference is very divisible by P to the N. And the idea behind it is that when you solve when you have congruences, if two numbers are congruent modulo large powers of P, you can start trying to solve a Diophantine equation modulo P square, modulo P cube. You will not be able to distinguish between those numbers until much later. So that's the idea. Now, what happens with this ring that collects all the embeddings of Q is that Q embeds in this ring discretely. And the reason that Q embeds in this ring discretely is that if two numbers are close in the p-adic topology, they're congruent modulo large power of P, they're very far from each other in the real topology. So two rational numbers can never be close to each other two distinct rational numbers can never be close to each other in every p-adic topology, including P equals infinity. And therefore, Q is some discrete, some lattice. So think of Z inside of R. It's a completely analogous picture. Q embeds inside of this ring of Adels. So let me recap, because this is not as complicated as it looks in the beginning. The ring of Adels is just a convenient way to package both the real numbers and congruences modulo various integers, prime numbers. So we package them at the same time. But here's what the nice thing that happens in that case. The nice thing that happens is that the Euler factor at P of the zeta function can also be written as a Mellin transform. Namely, because it has this series expansion, it can be written as the Mellin transform of the characteristic function of the p-adic integers inside of the p-adic rationals. And you can compare it with the extra factor that appeared, the so-called Archimedean factor that corresponds to P equals infinity, which is, by the definition of the gamma function, is simply the Mellin transform of the Gaussian. So the Mellin transform of the Gaussian is essentially the gamma function. Now we see that the Archimedean factor of the zeta function, of the completed zeta function, has exactly the same nature as the non-Archimedean factors, as the p-adic factors. Are there any questions at this point? Okay, so let me go one step further. So this repackaging by Iwasawa and Tate is flexible enough that it allows to include many more similar zeta and L functions. By the way, the L and zeta is the same, is a different letter that's used for the same kind of functions. So, for example, if you have a Dirichlet character, what is a Dirichlet character? You take the group of congruences modulo n, you take the invertible elements of Z modulo n, This is your group, and you take a character of this group, a homomorphism to C star. So this is called the Dirichlet character, and this will be a special case of what we will call automorphic forms. So there will be two sides in our story. There will be the automorphic story and the Galois story. This is the automorphic story. Anything that has to do with congruences, and I will give some more precise definitions later, but anything that has to do with lattices and congruences will be the automorphic story. So you start with this character, and then you slightly modify the zeta function by inserting this character. That's all. Up to some details that I haven't written down. Again, my expressions will be a little bit approximate, especially at points of ramification. So they will not be exact. But for the purpose of this talk, this is the definition, and it's fine. So you just modify the zeta function by multiplying the summand by this character. So this is called a Dirichlet L function, but this Dirichlet L function can also be seen as an L function attached to a Galois representation. Now we come to the other side, to the Galois side. How does this happen? It happens by identifying the group, the multiplicative group of Z mod n, with a Galois group, the Galois group of the field Q, where you attach the nth roots of unity. So there is an identification of the Galois group of Q with the nth roots of unity attached, and the with the multiplicative group of Z mod n, and the identification is as follows. An element of Z mod n star acts by raising a chosen primitive root of unity to the pth power. So instead of thinking of this group in terms of congruences, we can think of this group as a Galois group. And then the character that we started with is a character of the Galois group. So then this L function is attached to a character of the Galois group, a one-dimensional representation of the Galois group. And more generally, I'll introduce some more general L functions now, called the Artin L functions. If you have any finite dimensional representation of the Galois group, in other words, a homomorphism to the general linear group of a vector space, the Artin L function associated to this representation is again defined as an Euler product over all primes. So let's compare to the previous expression. The previous expression for Dirichlet characters was 1 minus chi of p to the minus s inverse. So here we have a higher dimensional Galois representation, but basically the place of chi of p is taken by the eigenvalues of a certain operator. And what is this operator? It is the representation applied to a particular element in the Galois group called the Frobenius. And the Frobenius looks like it's completely analogous to before. Before we saw that P as an element of the Galois group was acting by raising to the power of P. The Frobenius is some element that modulo P raises to the power of P or to minus P. I have put a minus here, but don't worry about this. There are different conventions here, but let's not worry about plus or minus P. But what you should keep from this is that the Galois group has these distinguished elements for every prime P called the Frobenii, and they act by a power of P. They are defined initially as element of the Galois group of a finite field, where they raise by a power of P or the inverse power of P, and then they are lifted to the Galois group. And the Artinian function encodes the eigenvalues of these elements under a given Galois representation. So between this slide and this slide, what I did is, when I started learning about L functions, I never understood why the determinant of 1 minus Frobenius times P to the minus S is the right thing to consider. Why is it a natural thing to consider? But you can see, so this is essentially a characteristic polynomial. And a nicer way maybe to think of this characteristic polynomial is the trace of Frobenius on the exterior powers of your vector space. So you take the representation of Frobenius on this vector space, but then it also acts on the exterior powers of the vector space. And you take the trace on these exterior powers, where this trace, so these alternating powers, in other words, where the trace is taken in the graded sense, meaning on odd alternating powers, it's taken with a minus sign, and on even ones, it's taken with a plus sign. So that's a nicer way to write down this characteristic polynomial, and will be useful in the future to think about these determinants as trace of Frobenius on some alternating powers of a vector space. Okay, so now let's talk about a similar kind of L functions, the L functions attached to algebraic varieties and Diophantine equations. So again, gamma will denote the Galois group of the rational numbers. And well, I'm going to describe something that's almost like a Galois representation, but it comes from algebraic geometry, from arithmetic geometry. So how do you obtain Galois representations from geometry? You consider the cohomology, the étale cohomology of some geometric objects, for example, elliptic curves. So the Galois group acts on this étale cohomology, and this gives you essentially a representation of the Galois group or something closely related that's called a motive. And using the recipe that we talked about before, you can define the L function, which in this case, in the case of elliptic curves, can be written also in a very elementary way, because the factor at P, of course, it can be written as determinant, as this characteristic polynomial of Frobenius, but it can also be written in terms of the solutions of this Diophantine equation, modulo P. So, and I think I wanted to, so let me just, I think I meant to give a name to this expression in brackets. So at the very end, you see this number that determines the Euler factor, P plus 1 minus the number of solutions to the Diophantine equation modulo P, the number of points of the elliptic curve modulo P. So this number will later be called AP. I should have included this in the slides. So the L function counts the solutions of the Diophantine equation modulo P for every prime P. That's what it does. Okay, so why are L functions important and why do we want to study them? They have many important applications in number theory. For example, the Riemann hypothesis will imply an error term in the prime number theorem, the distribution of prime numbers. The Birch-Swinnerton-Dyer conjecture will imply inequality between the rank of the group of rational points of an elliptic curve and the vanishing of the L function at the center of symmetry. So these are very important applications, and here's $2 million on the screen for you to solve. But really, I don't think that any of the applications by itself fully encapsulates the importance of the L functions. Their importance lies in the mysteries that they help uncover. They somehow mysteriously involved in all kinds of mysteries that we don't understand, and they help us uncover these mysteries. So usually we try to understand some conjecture involving L functions, and we discover something bigger than that. So one of these mysteries, which is the Langlands reciprocity conjecture, relates the L functions of Diophantine equations and motives that we saw before with the example of the elliptic curve to those of automorphic representations like the Dirichlet characters that we saw in the beginning. So now we'll talk about these L functions, the L functions of automorphic representations. I will talk about automorphic representations. So automorphic representations is, roughly speaking, what we get when we do harmonic analysis on arithmetic drums. So let me explain what this means. So when I say harmonic analysis, what I have in mind is a group acting on a space X. I'll write this as a right action. And then this induces a representation of the group on the linear space of functions on X by this formula. So G acts on F by translation. The prototype, of course, is the group R mod Z or the group R. And that's the Fourier theory that we all learn. In the case of R mod Z, Fourier theory will tell you that L2 of G decomposes into a Hilbert space direct sum of one-dimensional subspaces. And these one-dimensional subspaces, the exponentials, are precisely the irreducible representations for the translation action. If you translate an exponential, you get back the same exponential up to a scalar. The same thing happens with G equals R, but in that case, the exponentials are not in L2. So L2 doesn't decompose into a direct integral, direct sum, but what is called a direct integral of Hilbert spaces. Basically, this statement is equivalent to the Plancherel formula. And the Plancherel formula is the statement that the L2 norm of a function is equal to the L2 norm of its Fourier transform. But in this case, I'm not thinking of the function the Fourier transform symmetrically. I'm thinking of the function as my input, and the Fourier transform evaluated at a point t is the coefficient of the exponential at t that I get when I decompose my function into irreducibles, into a direct integral of irreducibles. So the right-hand side for me is, so to speak, the spectral side. The left-hand side is, so to speak, the geometric side, the function I started with. Now, the irreducibles here were one-dimensional because our group was abelian, but there's here's a classical non-abelian example. You can consider the n-sphere. This is a homogeneous space for the action of SOn plus 1. And you can ask, what are the irreducibles? How does L2 of the sphere decompose into representations, irreducible representations for SOn plus 1? And the answer, a classical answer, is it decomposes into an infinite Hilbert space direct sum of finite dimensional representations, and these irreducible finite dimensional representations are given by the harmonic polynomials of the homogeneous harmonic polynomials of degree k, the so-called spherical harmonics. So we want to imitate this example for more complicated spaces. Automorphic forms will end up being the analogs of the exponentials or the spherical harmonics for a more complicated space. So what is the more complicated space that we want to consider? It is the quotient of a reductive group like GLN by a lattice. A lattice is a discrete subgroup such that the quotient has finite volume, at least up to the center of the group. So maybe instead of GLN, better think of SLN. Then SLN has discrete subgroups with such that the quotient has finite volume under the Haar measure. So these are much more complicated spaces. In arithmetic, we're interested particularly in arithmetic congruence lattices. These are not arbitrary lattices, but they come from taking something like the z points of the group, or some finite index subgroup inside of there. So these are particularly interesting because they, when we do harmonic analysis, we don't just have the translation action of the group, but we have many more operators coming from correspondences. Namely, instead of translating by the group on the right, you can try translating by a rational matrix on the left. So a rational matrix like the one that you see at the very end here, diagonal P1. So if I translate by this matrix on the left, I will lose GLN Z invariance, but I will not lose it very much. So if I translate by this matrix on the left, I still have invariance by gamma of P, which is the matrix, the integral matrices that are congruent to 1 mod P. And this is a finite index subgroup inside of GLNZ. And therefore, what I can do is I can translate on the left by this matrix and then sum over the fibers of this, finite fibers of this map that you see here from x of p to x. And that gives me an operator on the set of functions on x, which is called the Hecke operator. So the Hecke operator is the operator that we get simply by this left translation and then integrating over the summing over the fiber. So automorphic forms for congruence groups come with a lot of these operators, one for every prime p at least, actually many for every prime p. And a nice way to encode the operators, like we said, a nice way to encode congruences is by passing to the ring of Adels. So topologically, this is a locally compact topological ring. So if you see this for the first time, you should think of the quotient that I denote here by brackets G, which is the G Adels mod G of Q. You should think of it as G of R mod G of Z. Topologically, they are very similar to each other. So the smaller subgroup is discrete inside of the bigger subgroup, and the bigger subgroup is a locally compact topological group. Okay, that's just a convenient way to encode the Hecke operators, and now the action of the pth Hecke operators translates to an action of the group G of QP on L2 of this space. So again, you might prefer the classical picture where we're talking about G of R mod G of Z. Everything translates to this classical picture, but it's a little bit more convenient to think of adelic groups so that we have an action of a bigger group. There's always, whatever you see in the following slides admits a classical translation, but it's a little bit complicated to describe. Okay, so now what does Langlands conjecture? So we saw that in harmonic analysis on these arithmetic drums, we get joint, we have a large collection of Hecke operators indexed by all the primes. And we can try to find joint eigenfunctions of those. The joint eigenfunctions of these operators will give rise to a collection of their eigenvalues. So here we get a collection of numbers AP, one for each prime P. We will call this the eigenfrequencies of the arithmetic drum. The two main predictions of the Langlands program are, first of all, that the eigenfrequencies of arithmetic drums often come from solutions of Diophantine equations or representations of Galois groups. In other words, the collection AP of eigenfrequencies of the arithmetic drum of some eigenfunction of the arithmetic drum is equal to the collection of numbers that enter the L function of the elliptic curve, and that I also called the AP before. So these are two completely different worlds that have nothing to do with each other, but conjecturally, well, a priori they have nothing to do with each other, but conjecturally, one can discover these arithmetic quantities coming from the elliptic curve in the harmonic analysis on arithmetic drums. This is, of course, not a conjecture in this case. This is the Taniyama-Shimura-Veil conjecture that was proven by Wiles, Taylor, and other people in this case. But in general, it's widely open. And the second conjecture of the Langlands program is that the same eigenfrequencies appear on different arithmetic drums. What does this mean? Well, the arithmetic drums depended on a group that we chose, and any one of these reductive groups has a so-called Langlands dual group attached to it. This is a little bit ad hoc, but let's move on. It doesn't matter. We'll see some examples in the next slide. So for any one of those groups like GLN, SLN, and so on, there is a Langlands dual group such that a homomorphism of Langlands dual groups gives rise to a map from eigenfrequencies of the first group to eigenfrequencies of the second group. So any homomorphism between the dual groups should correspond to a matching of eigenfrequencies for arithmetic drums of these groups. Are there any questions, by the way? Okay, I should pause a little bit. Okay, so I said you will see dual groups in the next slide. It's a little bit later, I'm sorry. So let's say a word about automorphic L functions. So in the previous slide, we said that motives and Galois representations should correspond to automorphic forms by this recipe of eigenfrequencies. So where are the L functions on the automorphic side? An ad hoc definition, but you cannot use it to prove anything. Like you cannot use it to prove analytic continuation like Riemann did, for example, or functional equation, is to just take these numbers AP and plug them into the L function exactly the same way that you did on the Galois side. But on the automorphic side, there are actually more useful presentations like the one that we saw of Riemann. So our goal is to understand those presentations. Our goal is to understand where these presentations of L functions come from, the ones that help us prove something about them. So let me give another example of a way to write an L function as an integral. For suitable subgroups H and G, so now we're doing automorphic forms for a certain group G, for example, GLN, okay? But we will see other groups as well. So for suitable subgroups, there are conjectures expressing the period integrals of automorphic forms over those subgroups in terms of L values. And a large such class was described by conjectures in the last 10 or 15 years by Gan, Gross, and Prasad. Actually, the first conjectures were more than 15 years ago. And they have to do with the group SON times SON plus 1, and the subgroup SON embedded diagonally. So then the conjecture of Gross and Prasad, and then refined by Chino and Nikeda, says that if you take these automorphic forms that live on the arithmetic drum of G, and you restrict them to the arithmetic drum of H, which is a subspace of the arithmetic drum of G, and you integrate it over them, then the absolute value square of this integral is equal to an L function, or more precisely, a special value of an L function. Now, if you don't know the notation on the right-hand side and what the tensor product is doing there, I am going to explain this in a following slide. But what you should keep from here is that if you take eigenfunctions, so automorphic forms, on the arithmetic drum of G, and you integrate them over a smaller arithmetic drum that lives there, then the absolute value square of that is equal to an L function, conjecturally. So in the unitary case, if you replace orthogonal groups by unitary groups, this conjecture has been proven now by Wei-Zhang, Berzat-Plessis, Liu, Zhu, Chaudhua, and Zidor, using a strategy of Sakellaridis. In the orthogonal case, this is a very open conjecture, and it is very important for number theory. Now, it looks like, so actually the simplest case of this conjecture goes back 100 years to Hecke. Classically, we think of automorphic, the most classical example of automorphic forms is modular or mass forms on the upper half plane. So if F is a mass form on the upper half plane, then the integral that you saw in the previous slide is just an integral over a geodesic, the vertical geodesic from 0 to infinity. So this is a very classical construction that you may have seen, that everybody says when they learn about mass forms and modular forms. What we saw is a generalization of that. But if you compare it with Riemann for the zeta function, the two expressions don't look the same. Both are some kind of Mellin transform, but that's a little bit misleading. They're Mellin transform of a different thing. In the first case, it's a Mellin transform of an automorphic form. In the second case, a Mellin transform of a theta series, which is not quite an automorphic form. It's not like an eigenfunction for the Hecke operators or something. So, but there's a quite formal translation of the first integral, and I'm not going to explain it, but it's the kind of thing where I ask you to believe that, yeah, the first integral can also be written in terms of a theta series. And it's quite formal, so I'm not hiding something deep from you. It's just another way to write it. So, like with Riemann, we write a theta series on a certain space. Now, the theta series, I will explain what theta series means. I'm writing here everything adelically. So what I do is I take the space G mod H. So we had the group G, we had the subgroup H, and I'm taking the space X, which is G mod H. And this is some kind of affine variety. So in this low rank example, this is PGL2 mod GM. It's like a hyperboloid. And I'm summing some Schwarz function over the rational points of this variety, of this adelic variety of field. So this is some kind of discrete sum of a rapidly decaying function. So it will converge. It's a theta series, and it looks like Riemann's or Jacobi's theta series that appears in the previous integral. And then I'm integrating it against an automorphic form. And that's a complete analogy now with the Riemann case, because the automorphic form, like we said, is the analog of the exponential, is the analog of an irreducible representation. So in Riemann's case, the irreducible representation is a multiplicative character, y to the s over 2. Here, the irreducible representation is represented by this f of g, which is supposed to be an automorphic form. So the two integrals start looking the same. We have an automorphic form. In the first case, it's y to the s over 2. In the second case, it's f of g. And it's integrated against some theta series, but this theta series comes from a different space in each case. So where do these theta series come from, and which L functions do they encode? This is the question that we're trying to answer. So let me now try to explain what it means. I wrote before an L function, a certain L function with a tensor product notation. So let me explain what this means, because this will be important for the formalism that follows. So I mentioned this dual group that appears in the Langlands program. The Langlands correspondence aims to understand representations of a group G over a local field like R or QP, or automorphic representations of G when defined over a global field, in terms of roughly Galois representations into the Langlands dual group. And here's an example of Langlands dual groups. So the dual of GLN is GLN, but the dual of SLN is PGLN, the dual of SO odd is SP, and so on and so forth. And this is involutive. So this is a little bit ad hoc again, but that's how it is. And the dual group is a non-abelian adaptation of the Pontryagin dual of abelian Fourier analysis. So we have already seen abelian Fourier analysis in this talk. It generalizes to arbitrary locally compact abelian topological groups. I should have said abelian here. So by definition, the points of the Pontryagin dual are irreducible representations, characters of unitary characters of the group. But the duality in our case, very significantly, it's not so simple. You cannot describe the dual group in terms of characters of the original group. The groups are not abelian. And the conjectures, the local Langlands conjecture says that invokes the Galois group. So roughly speaking, it says that irreducible representations of G of F, now F is a local field like R or QP, more or less up to some equivalence relation, are parameterized by representation of the Galois group with imagine the dual group of G. So more or less, that's what the local Langlands conjectures say, that irreducible representation of a group like GLN-R or GLN-QP are parameterized by Galois representations into the dual GLN. Now, now I'm going to explain what it means to have a tensor product L function. So given an automorphic representation of G, its automorphic L functions will be parameterized by finite dimensional representations of the dual group. So what happens here is that we want to construct a Galois representation in the end, a linear Galois representation on a linear space. So the way we do it is we compose the map from the Galois group to G check, which was associated to the automorphic representation or to its local components, with a finite dimensional representation R of the dual group. So it's very important to keep in mind that there is not just one L function associated to an automorphic representation, but a whole infinite collection of them parameterized by representations of the dual group. So for example, in the conjecture that we saw before, our group was SO2n times SO2n plus 1. Its dual group is SO2n times SP2n. And the L function is associated to the standard tensor product representation of this dual group. So SO2n and SP2n belong both to GL2n, and then you take the tensor product of their standard representations. So this gives you the data of some Galois representation at every p-adic and real place, and you combine those into the Euler factors that we saw before. Let me pause again to see if there are any questions. I would really like to receive questions. I don't. No?
Yeah, all looks good.
Okay. So here's the plan for the rest of the talk. I'll present a conjectural interpretation of the automorphic L functions based on joint work with Ben-Zvi and Venkatesh. Now, this works over function fields. What is function fields? It's a function field of a curve over Fp. But these are analog to number fields, and they can help us understand L functions over number fields as well by some analogy. And this work refines and categorifies earlier conjectures that I had with Venkatesh, but the categorification is something that I will not be able to show you today. So most of the things that I will say go back to earlier conjectures, but the general picture involves a symplectic duality of Hamiltonian spaces. So Hamiltonian spaces for G and Hamiltonian space of G check. So what is a Hamiltonian space? Hamiltonian space is a symplectic variety with an action of G, where the infinitesimal action of G is given by a moment map. Now, none of this will appear very much in the talk, so I'm suppressing it. Just think of symplectic spaces with G actions, okay? And this symplectic duality, this conjectural symplectic duality, underlies the correspondence between the L functions on the Galois side and the L functions on the automorphic side, which will be represented by integrals like Riemann's. So I think I'll skip the philosophy of quantization that I have here because it's not essential. It's not very essential. And I'm going to be a little bit short of time. So the only thing I want to say is that to these Hamiltonian spaces, if you have some symplectic manifold with an action of the group G, it's a classical problem that's coming from quantum mechanics to associate to it some Hilbert space. So this is the passage from classical Hamiltonian mechanics to quantum mechanics. You start with a classical system that's realized on some Hamiltonian manifold, and then you want to quantize it, which means that you want to produce a Hilbert space. Now, if this Hamiltonian manifold had an action of a group, the quantization should also have an action of the group. So you should get a unitary representation of the group. Now, the examples that I will talk about are usually very simple. So very often our manifold will be the cotangent space of X for some G space X. And in that case, I don't even need to talk about quantization. I could have started with X and said, okay, let's consider L2 of X. The reason I'm talking about quantization will appear later, and it is that I need to include some other symplectic spaces that don't admit this description. For example, the standard symplectic representation of the symplectic group, which gives rise to the veil representation. This is not, if I take a symplectic representation, if I take just a symplectic vector space, you can think of it as the cotangent space of a Lagrangian subspace. But this description is not invariant under the group SP. So it's not a cotangent space of a G space. Okay, so for some reason, it's not enough to think just about cotangent spaces, but for simplicity, most of my talk will be about cotangent spaces. So let's take a symplectic G space M, which is the cotangent space of X, where X is a G space. And then the quantization of it is L2 of X, okay? So we don't need to worry too much about it. Now, the philosophy that we have is that one should look at an automorphic realization of this quantization. And the automorphic realization is precisely the theta series. So if I give you a space X with a G action, a nice space, let's say affine, then you can write down its theta series. Classically, it would be written as a sum over the Z points of X. Adelically, it would be written as a sum over the Q points of X. So you start with a Schwarz function in your space and you take its theta series. And that produces for you an automorphic function like the Jacobi theta series that we saw before in Riemann's case. Sorry. I changed the variable a little bit from y to z, which is the square root of y, but that's essentially the Jacobi theta series. So this is the example of the Jacobi theta series. My space is the affine line. My group is GL1. And I start with a Schwarz function on that space. And I sum it over the Z points of that space. That gives me the theta series. The Schwarz function happened to be the Gaussian in that case.
So in relation to earlier slides where you were discussing Ichino-Ikeda, so should we think about this X as G mod H or something?
Yes, in the Ichino-Ikeda case, this X is G mod H.
But this is more general, you're saying. You don't need that.
No, so there's always going to, what is more general?
I mean, you can just take any X with, like, we're on with GX, basically. You don't care if it arises in the form G mod H.
Yes, it doesn't have to be homogeneous. Yes, exactly. So in this example, it's not homogeneous. The group is GM, but X is A1. Yeah, so it has to be a nice X, and I'm gonna push it all under the carpet. It has to be, for what we have done, it has to be spherical and satisfy some other conditions, but I'm not gonna worry too much about that. I want to give you some sense of where this theta series come from. So given an affine G space over F sufficiently nice and a Schwarz function on this space, on the adelic points of this space, we define its theta series with this recipe. We just sum over this discrete subset. And then this produces an automorphic function. This produces a function on G of A mod G of F. So this construction is very common in number theory, and it has tons of names depending on which space you start with. Not just the Jacobi theta series that we saw before. For appropriate spaces, it produces Poincaré series, it produces Eisenstein series, it produces the theta series of the Weil representation. Many classical constructions fit into this formalism of theta series. Okay. Now, what I want to claim is that some of these theta series encode L functions. So, but before I do that, in order to get towards our work, I need to introduce function fields. So our work, like I said, makes sense over function fields, but by analogy, it can be understood over number fields as well. So an example of a function field is just a function field of rational functions over Fp, over the finite field Fp. These are considered as the rational functions on the projective line. Okay, so there's this analogy between Q and function fields of curves over Fp. The primes in Q are the primes. The primes in the function field are the points of the curve, the points in the scheme theoretic sense. For example, again, for the function field of rational functions, the primes are simply the prime ideals in the polynomial ring union with infinity. So these are the primes, the prime ideals in the polynomial ring plus the point at infinity. So for a function field, we have the notion of ring of integers like Zp at every place V. And I will denote by O hat the product over all places of these ZPs, of these rings of integers. The benefit I have over function fields is that I have a distinguished Schwarz function. So I don't have to choose a Gaussian or something, because every place here is non-Archimedean, like the p-adic numbers. So I can choose the characteristic function of the integers. So this gives me a distinguished Schwarz function. And then out of this Schwarz function, I form a theta series. So out of the Schwarz function of the integers of some nice G variety, I form a theta series and I get an automorphic function. In the function field case, this theta series also has a geometric interpretation, because now this is a function on the adelic modulo rational points of the group, modulo on the other side, which is invariant by G of O hat. And this space admits a geometric description as the moduli space or the set of isomorphism classes of principal G bundles on the curve. So for example, for GLN, this double quotient of the adels is the set of isomorphism classes of rank n vector bundles over the curve. And let's do GL1. In the GL1 case, and let's try to study this theta series over GL1. In the GL1 case, the group is the multiplicative group. We take our space X to be A1. Ban-G is the Picard group, the moduli space of line bundles on the curve. And to any line bundle on the curve, you can associate the vector space of sections of this line bundle. And this gives rise to a function on Ban-G, where for any line bundle, you count the number of sections of the line bundle. And I claim that this is precisely the theta series. So the theta series now is a function on the space, on the isomorphism class of line bundles, and it counts the number of sections of the line bundle. I'm not going to prove it here, but this is an exercise in representing line bundles by divisors. That's all that it is. So how do you represent line bundles by divisors? How do you identify line bundles with divisor classes? If you think about it, you will prove this formula, that the theta series counts the number of sections of the line bundle. And this is precisely the analog of Riemann's theta series, or Jacobi's theta series, in the integral representation of the zeta function. So to recap, the theta series over function fields also have this geometric meaning. They count sections of something. So now we define the theta series, and we conjecture that for good spaces, it is the automorphic incarnation of some L function. That means roughly that if you do its Fourier transform, but Fourier transform here in the non-abelian sense, if you decompose it into irreducible representations, which we have called automorphic, then the Fourier coefficients are certain special values of L functions. That's what it means. So we conjecture that, and again, I'm not saying what good spaces means and all of that. I just want to give you the general feeling and the general picture that for nice spaces, we have theta series. These are automorphic functions, and we decompose them into irreducibles. And the Fourier coefficients of these automorphic functions will be L functions. This is the conjecture, that the L function is encoded in the theta series. It just it's the Fourier coefficient of some theta series. So again, here is Riemann's example. We wrote down the completed zeta function as the Mellin transform of some theta series. And that means that the Plancherel density is the absolute value square of the completed zeta function. That's what it means. So the question is, what L value appears on the right-hand side above? What is L of pi? This is still unspecified. So I start with a good space X. Which L function am I getting? Let me also go back again to function fields to give you a topological picture. So actually, maybe I'm running out of time, so I'll just quickly say that I'll quickly say the following thing. If you have a curve over a closed over the algebraic closure of Fp, then a nice geometric way to think about, to imagine it, is as a Riemann surface. It's the analog of a Riemann surface when you replace the complex numbers by FP bar. When you have a curve over Fp, so defined with coefficients over Fp, the nice geometric picture is to think of it as a family of Riemann surfaces over spec Fp. And spec Fp, because the Galois group of Fp is generated by a single element of Frobenius, spec Fp is a nice way to think of it is as a circle. So topologically, a curve over Fp is something three-dimensional, which is like a family of Riemann surfaces fibered over spec Fp. So let's look at this diagram a little bit here. Sigma is the curve over Fp. Sigma bar is the same curve, but thought of over Fp bar. And we have fundamental groups. We have some kind of universal cover, and the fundamental groups fit into the short exact sequence where the quotient is generated. The quotient is the Galois group of the finite field. So the quotient is generated by the Frobenius element. So that brings me to the geometric side, to the Galois side of our story. If I have a Galois representation of the Galois group, which here is not going to be the full Galois group, it's going to be just the fundamental group of my curve, I can think of it as a local system on my curve, which is the same as a local system on the Riemann surface with an action of Frobenius. And then it is well known that the L functions, by an application of the Grothendieck-Lefschetz fixed point formula, the Artin L functions that we saw before can be written. Let's look directly at the very last line. The Artin L functions can be written as a trace of Frobenius on the cohomology of this local system over the Riemann surface. By Riemann surface, I mean the curve over Fp bar. So let me recap for a moment. I start with a Galois representation. We know that this gives an Artin L function. And using the Grothendieck-Lefschetz fixed point formula, this Artin L function can be expressed in terms of trace of Frobenius on the cohomology of the local system on the curve over the algebraic closure of Fp, or rather the exterior powers of this cohomology. So our philosophy will be that the L function of this Galois representation, or of the local system, is represented by this collection of graded vector spaces, the exterior powers of the cohomology of the local system over the Riemann surface. These vector spaces with Frobenius action are a more refined object than the L function itself. So on the Galois side of our duality, we have the following data. So again, you have a smooth projective curve over a finite field Fp. We started with a reductive group over Fp, and now we want to answer the question of what is the L function. So we started with a group G, and we started also with a theta series attached to a nice space for G. And we want to say, what is the L function associated to this theta series? So we have to think of the Langlands dual group, and recall that every representation of the Galois group, sorry, this is repeating the previous slide. So let's look at the last item here. So on the dual side, we're also going to have the dual group G check together with a space on which this acts. And out of this data, what I want to do is I want to extract something that's like an L function. How do I extract an L function from a dual group and a space on which it acts? Well, if you think about the linear case that we discussed before, the L function is extracted as trace of Frobenius on the cohomology of a local system. So what is cohomology? Cohomology is sections, okay? And if you think of the local system as coming from a Galois representation, sections is the same as fixed points under the Galois group. But sections and fixed points in a derived sense. So H0 means fixed points under the Galois group. Hn is some derived version of sections. So again, to take a step back and explain what I'm doing, I'm saying that like in the linear case, where we had a Galois representation and we encoded the L function in the trace of Frobenius on some space, which is the space of sections of the corresponding local system or the space of invariants of the Galois representation. Similarly, for any G-check space X-check, and for any representation of the fundamental group into G-check, we can consider the invariance of the fundamental group acting on X-check through this representation. And this gives me some kind of derived space that also encodes some kind of L function. And this will be our geometric realizations of L functions. So Frobenius trace on some sheaf associated to this derived invariance can be interpreted as an Artin L function. So I understand that this is a little bit fast because I'm over time, but let me just say that on the automorphic side, we have a space X, and it gave us a theta series. And on the spectral side, we're going to have a space X check for the dual group G check. And through this process of derived invariance, it's going to give us the data that we need to define an L function. And now we conjecture that for a nice class of spaces on one side, we have a corresponding space on the other side, such that the theta series on one side matches the L function on the other side. Now, I'm formulating this conjecture not in terms of the space X, but in terms of a Hamiltonian space M, which could be its cotangent bundle. And the reason I'm doing it is that it's not enough, like I said, to consider cotangent bundles. We have to work with a slightly larger class of Hamiltonian spaces. But let me give you here, because I'm over time, let me give you here a table of examples where you will see a Hamiltonian space with an action of a group G on one column and a Hamiltonian space with an action of the dual group on the other column. And these two columns encode examples of the phenomenon theta series is equal to an L function, where you can put the theta series on either column and take the L function on the other column. So each column encodes either a theta series or an L function, and then the conjecture, which in this case that I wrote here is mostly a theorem, is that the Plancherel density of the theta series is expressed in terms of the L function encoded by the other side. And I think I need to stop here. I had a slide with some relations to mathematical physics, but maybe that's a little bit too far for now. I went a little bit slower than I thought. So let me stop at this point.
Thank you, Yiannis, for this really nice talk. Questions for Yiannis?
Maybe I ask a question. We define the local L factors. How about do we define also epsilon factors as well in your theory?
Yeah, that's a very good question. So the answer is no, first of all, but let me tell you some idea about what epsilon factors, about certain epsilon factors. Like I stressed a few times, there is a reason why we need to work with Hamiltonian spaces and not just with arbitrary G spaces and their cotangent bundles. For example, let's look at the fourth line of this table, where on the left it says Galois-Prasad and on the right it says theta correspondence. Okay. What does it mean that it says Galois-Prasad on the left-hand side? It means that if you want to construct the corresponding theta series, it will essentially correspond to the integral that I showed before of Ficino-Ikeda. And the absolute value square of this integral is conjectured to be related to the L function that you see on the right-hand side, namely the standard tensor standard representation of the dual group. But this is for the absolute value square of the L function. So one might ask, what is the value of the L function itself? Can I relate that to an L function? Now, if you look at the right-hand side, this is the non-polarized case that I was saying. It's not a cotangent bundle of a G space, of a G-check space, which means that there is no obvious way in which you can write down this L function as the absolute value square of something. If this were the cotangent bundle of something, then you would be able to write it. We saw it in the Riemann case. In the Riemann case, the Plancherel density was the absolute value square of the zeta function, of the completed zeta function. Here in the Ficino-Ikeda case, this is not the case. The absolute value square of the theta series is equal to a single L value for this L function, which cannot be written as an absolute value square of something. So, and the reason again is that we don't, our dual Hamiltonian space is not a cotangent space. So there is a need to write the dual Hamiltonian space as a cotangent space, but this you cannot do. So on the automorphic side, this problem has been resolved by the theory of the veil representation. The theory of the veil representation gives you a way to produce the quantization, even if your space is not a cotangent space, not for arbitrary Hamiltonian spaces, but for example, for linear symplectic spaces, for example. So even if that space is not cotangent of some G space, you can still produce a representation, and this is called the veil representation, at the expense of maybe having to move to the metaplectic group. On the Galois side, we don't have this yet. We don't have a notion of veil representation on the Galois side. But we do know from the Galois-Prasad conjectures that epsilon factors control the local problem of decomposing L2 of X in this case, where X is again this G mod H. So we know from the Galois-Prasad conjectures that the epsilon factors kind of decompose, determine the decomposition of L2 of X. So if you wanted to define a square root of this L function, you would have to see some epsilon factors appearing. But I don't know how to do that. That's my answer.
Any other question? Yeah, maybe I'll ask you a couple of questions with this about the slides. Can you go to slide number 25?
Yes.
I guess about the, what is, I mean, can you say something about X check, at least in the homogeneous case? What kind of
Actually, thanks a lot for giving me the chance to go back to the slide, because this is where I didn't have time to explain a lot. So again, I want to encode the L function in some G-check space, okay? So if that G-check space is linear, then we know what this means. So if I have a linear representation, if I have a linear representation of G-check, then I can compose it with any, I can think of the action of any Langlands parameter on that and take invariance in the derived sense. That means the cohomology group, and then the trace of Frobenius on that will give me the L function. Okay, so that's when X check is linear. So when I have a G-check a linear G-check representation, I can associate an L function to it. Basically, that's something that I already said earlier in the talk. I said that L functions are parameterized by linear representations of the dual group G-check. Okay. Now I'm claiming that this needs to be generalized a little bit. it's not going to be just linear representations of G check. It's going to be more general space for G check action. Okay, and this more general space I denoted by X check, although like I explained previously, that doesn't capture everything. We need to think of cotangents of Hamiltonian spaces, but in many cases it is just X check. So what is the meaning of this X check? For example, if X check is homogeneous, for example, in the previous slide, we saw many X checks which were homogeneous. The slide here tells us that we should consider, for a given Langlands parameter or for a given representation of the fundamental group, we should consider the derived invariance of X check. Okay. Now assume that X check is homogeneous, like G check mod H check. What would be the derived invariance in that case? Well, if the Galois representation does not have image in H check or a conjugate of H check, then there will be no invariance. So the fact that I'm using more general spaces means that I'm restricting my dual group to a subgroup. And this is a phenomenon that is well known from the relative trace formula, the work of Jacquet, and the problems of distinction and periods, that very often, in order to talk about theta series on one side, or spaces X equals G mod H on one side, you have to restrict yourself to a subgroup of the dual group on the other side. When the space that you started with is spherical, that subgroup is called the Gates-Corin-Adler dual group of the spherical variety. So given a space X on the automorphic side, there's going to be a space X check on the spectral side, which leaves over G check modulo the Gates-Corin-Adler dual group of X. So that's one function that this dual space X check has. It forces the parameter to land inside of a certain subgroup of the dual group. In other words, it detects some kind of Langlands factoriality from a subgroup of the dual group. And this is the most important difference between the linear case and the general case. The most important difference between the two cases is that the parameter is forced to live in a certain subgroup of G check in general.
And so this construction only is available in the geometric case?
This construction is only available in the geometric case because if you see, I'm taking invariance for the geometric fundamental group. Right. And then I'm applying trace of Frobenius. And this two-layer, this way to filter the Galois group only exists in the geometric case.
I understand, but you don't have any other way of, any other way of going about this to define this in the, in a number field case, basically, right now. You envision, a way of defining.
No, I mean, you can define the L function. Right. You can define, the L function can always be defined. Okay, you just don't have this nice picture that the L function is given by the derived invariance of some variety.
Okay. Yeah. Other questions? Yeah, maybe I'll ask one more if Yiannis is not too tired already. So what kind of, do you allow all weights in your, for your automorphic forms? Or do you have to work with some smaller class of weights, like cohomological weights?
No, definitely there's no arithmetic requirement. So first of all, we have to clarify which conjectures we're talking about, right? So in the work of with Ben-Zvi and Venkatesh, everything is over a function field and at the unramified level.
I see. Okay, yes. Okay.
And then the conjectures that we formulate are actually one categorical level up from what I described here. Instead of L functions, you have certain sheaves, and then you, instead of theta series, you have again some sheaves, and you conjecture that they match under geometric Langlands duality. That was a little bit too much to describe today, but I just described my goal was to describe like something function theoretic, but to give you an idea of these dual spaces that play a role. Now, if you want to go back to earlier conjectures, then and if you want to make these conjectures a little bit precise, because I was not very precise in stating the conjectures here, then in my earlier work with Venkatesh, we formulated these conjectures only for the so given a space, a G space X, we formulated conjectures only for the most tempered part of the automorphic spectrum that is not killed by the theta series.
I see.
Which, for example, in the Gross-Prasad case, is just the tempered part of the Gross-Prasad conjectures. Now, I believe, and I think in the Gross-Prasad case, it's already been done by Wittek-Gunn and maybe with a student of his, I don't remember, that this geometric picture can provide a way to approach the non-tempered cases as well. But this is something that has not been studied systematically yet.
I see.
So it's always a mystery how you go from the tempered case to the non-tempered case. For example, if you talk about the Whittaker period, so then conjecturally there are no non-tempered automorphic representations that are generic, right? That's the Ramanujan conjecture. That all generic automorphic representations are in L2 are tempered. On the other hand, if you think of Gross-Prasad, you have some conjecture for the tempered case, and then you have some slightly less precise conjecture also due to Icino and Kelda for the non-tempered case. They don't, the non-tempered case representations do not die in that case. So you see that there seems to be no general pattern at first. So in some cases, it's only tempered representations that survive. In the other cases, there's also non-tempered ones. But we believe that with this geometric picture, where you don't just assign a dual group to your period, but you assign a whole dual space, this phenomena can be encoded into that. But except for a few examples, we don't have a general theory for that.
Thanks. Any other question? I guess not. So let's thank Yiannis again for this really nice talk.
Thank you. Oh.
All right.
Yeah. That slide.
Thank you. Perfect. So I guess, yeah, we can probably stop recording now.